Hello, welcome back to CSC 263 Database Management Systems at Adelphi University. In the previous few videos, we talked about database security as one of the services provided by the DBMS. The DBMS has to worry about security because one of its other functions is concurrency, where it will allow multiple database applications and multiple users to interact with the database at the same time and typically via a network. And we want to make sure that that is done within responsible boundaries. Today, in this video, we'll look at a little bit more detail about other internal functions that the database management system provides. So specifically, the other database internal functions that we'll consider are transaction support, recovery, concurrency control, and to an extent indexing. So data integrity was that property where we said that data needs to be correct at all times, and whether that is because of the built-in rules that talk about domain integrity, entity integrity, and referential integrity, or is it because that we've added security controls to who can make modifications. Data integrity is paramount in our database. We want to make sure that only authorized changes are made by authorized people and that we're not violating the schema in any way, shape, or form. What we also want to do is not just worry about the schema enforcement, but also about the data itself. And when it comes to data security and data integrity more specifically, transactions play a key role in that. So the easiest way to think about a transaction is that we're just going to take a few queries and bundle them together. And then from that point, that bundled group of query is considered to be one logical unit of work. And since it's one logical unit, it can't be subdivided any further. So for example, I might have a few inserts paired with an update and a delete query. At the same time, I want to make sure that if I execute this bundle of queries, the bundle executes as a whole or it doesn't execute at all. So that's what a transaction is for, to make sure that we can bundle operations into a single logical unit of work. And that means that we can have two outcomes of that logical unit of work. Either it worked or it didn't. Specifically, if it worked, we call it a commit. We have taken the transaction, we've processed it, we did not interrupt any issues while we were processing it, and at this point the changes that are part of that logical unit of work are now committed to the database, and that means from that point on they are persistent. And that means that when I come back at some later point, the changes are still there as a whole. The other option could be that something went wrong, and whether it's something went wrong because of an abort or because of a violation of an integrity rule or a security constraint, it doesn't matter. Something went wrong, and at that point we want to be able to roll back. And specifically, let's say that we have a 4-step operation and steps 1, 2, and 3 completed successfully, step 4 failed. At that point, the transaction as a whole has to fail because that's the consequence of being a logical unit of work. But it also means that the operations step 1, 2, and 3 have to be undone. They have to be rolled back. And that is the role of the transaction mechanisms. So let's take an example here. Let's say that we want to give everyone a salary increase of 2.5%. And so we want to make sure that, let's say we have 100 employees, that we don't have to start with employee 1, update the database, do employee 2, then do the database, etc. Because invariably what's going to happen is that by the time that you've done the first 20 employees, the last 20 who haven't done anything yet will be on the call all angry, like, hey, why did he get a salary raise and I did not? Or why did she get, a new title and I did not? Once you start processing those, you want to process all of them at once. And if you bundle them all into a transaction, you can do that, because that means that either all of them will succeed at the same time or none of them will succeed. The other option could be thinking about our example that we've been running with, the students, the grades, and the courses. Now let's say that I'm going to change a student's ID number in the database, specifically in the students table. If I do that, let's say in my example here, I was student ID number 1. I'm going to give myself student ID number 100. The database is going to refuse that because it's going to see that there is already a grade assigned to student ID 1 and I'm taking student ID 1 away. I'm making a change in one table that isn't reflected yet in the other one. I can't fix it by doing it the other way around, because if I would go do it in the grades table first, and I'm going to say, oh, let's update this grade to student ID 100, the referential integrity rule is going to say, well, that student doesn't exist. So I need to do both of them at the same time. I need to update the ID number in the students table, and I need to also update the ID number in the grades table. And they have to happen at the same time, or fail. Transactions can help with that as well. So, a lot of research has been done in terms of transactions, and what we've arrived at is that if we're dealing with typical, relational databases, nothing fancy between distributed or databases or any of that stuff, we can say that a transaction must have 4 main properties that you can remember as ACID, A-C-I-D. And those stand for atomicity, consistency, isolation, and durability. And so what does that mean? Atomicity is the all or nothing rule. It means that all operations in the transaction will complete successfully, or none of them will. And that's an important one. So that means that we have to have this whole rollback mechanism in place. Consistency means that at the end of a transaction, you cannot leave the database in an inconsistent state. None of the rules may have been violated. Third property is isolation, and that means that any changes that are intermediate changes that are part of the transaction should be invisible to anyone else who's using the database until the point that the transaction commits. So in the example of my changing my student ID number, let's say that I've updated inside the transaction my student ID number to 100, but I haven't updated the grades table yet. For me, when I select from students, I will see my updated number. Anyone else who is not part of my transaction and who will at that point be querying the students number table will still see the old number. That's the isolation property. Only when the commit completes successfully will everyone else see the sum, the accumulation of all the changes. And then lastly is durability. Once the commit has been communicated to the end user, it has to be permanent. You can't renegotiate after the commit has been successful to say that my transaction needs to be undone. At that point, that would have to be done through a new transaction. Transactions play a very key term, not only in data integrity, but specifically when it comes to concurrency. Again, concurrency means that we have multiple database applications manipulating the same data at the same time. That is potentially a recipe for disaster, and so we have to find a way to deal with that. There's a couple of problems that are described pretty extensively in the book. The lost update problem, the uncommitted dependency problem, and the inconsistent analysis problem. And so let's take a look at each of those problems and see how transactions can help solving them. Let's take a look at this, this table here. It's called the lost update problem. So what we see is a number of columns. The first column is just a time index. You can think of them as discrete steps, steps 1 through 6. Then the second and the third column are the operations in 2 different transactions. T1 is one transaction, T2 is the other. And then balance X is the state of the database as seen from the database at the end of each of those time slots. So, T1, the beginning of the first time slot, transaction 2 initiates its operation. And at that point we know that the field balance contains the value of 100. At T2, now we have concurrency going, 2 things happen at the same time. Transaction 1 begins that transaction, and in transaction 2 I'm going to read the value of that balance. Now at this point, upon completion of step 2, transaction 2 knows that the balance is 100. It has read it, it has processed this, nothing has changed yet. Transaction 1 doesn't know that yet, because not until the completion of step 3, in which transaction 1 is reading the balance, which it then also knows is 100, will transaction 1 know that. But since transaction 2 already knew it, it's a step ahead, and at that point transaction 2 may have increased that balance by 1. Internally, in its transaction. That transaction has not yet been committed to the database, so the database still has it as 100, even though transaction 2 thinks it at this point it's 200, while transaction 1 still thinks it is at 100. At T4, transaction 1 does its operation. It figured out that the balance was 100, and it's going to decrease it by 100. So at the end of T4, transaction 1 believes that the value of balance is 0. Transaction 2 has already updated its belief. It now believes that the balance is 200, and it is ready to make those changes persistent in the database. It's going to write them. And at the end of that, the database will also believe that the value is 200. Transaction 1 never knew about this, so they've updated their belief that the balance is 100 minus 100 is 0. And now they are ready to write their value 0 to the database. And so they're updating the database again. Now the database believes that the value of balance is 0. And then transaction 2 says, I'm done, commit these changes. And even though transaction 2 believed that it had committed at a value of 200, by the time it hits the commit, it will be at 0. And the same thing will be true for T1. So what we've seen is that at this point, the update provided by T2 is completely lost. This is the lost update problem. And of course, this is not a situation we want to be in. Now we have a slightly different situation here. This is the uncommitted dependency problem, not the lost transaction problem. The lost update problem, sorry. At this point, we're no longer going to assume that isolation exists. At this point, we're going to believe that as we're making changes, those changes are visible across transactions. So again, at T1, the second transaction, T4, begins. Balance is 100. It's going to read it, still 100. It's going to increase it by 100, but it's only increased within the scope of the transaction. It's not increased in the database itself. So the database believes it's still 100, even though T4 might believe at this point that it's 200. At the beginning of T4, T3 begins its transaction, but T4 is ready to make its changes to the database, 200. And at that point, it's going to read from the database the balance, which is 200. It's been changed in the database, even though the change hasn't been made yet. And it's going to use that knowledge of 200 to update the balance to, say, 190. At that point, for whatever reason, T4 decides to abort its transaction and roll back its changes. So T4 wants to put the balance back at 100. T3 already recomputed the new balance as 190 and is ready to now go write this and commit it to the database. And just because T4 made changes that were visible before the end of the completion of the transaction, either through commit or a rollback, T3 is now updating the database with information that should have been different. And so that's a problem there as well. Now, one way we can do that is by using locks. And the name kind of says it all. You know, a lock means that you can't get in if it's applied. And so it's a procedure to use to control access to data in concurrent utilization scenarios. If you're only dealing with one process at a time, and you have a guarantee that there will never be a situation that multiple processes or multiple programs can be operating on the same data, you don't need this, but you cannot have that guarantee in most cases. So the database world came up with two solutions. One of them is called a shared lock, and the other one is called an exclusive lock. In a shared lock, it means that everyone else can still read the data, but they cannot make changes to it. So we're sharing, but we're sharing only read access. If I'm taking an exclusive lock, no one else can look at the data or manipulate it unless except me. And so shared locks, sometimes known as read locks, exclusive locks, the other one. So if you're going to access these data items and make changes to it, you should first apply one of those locks so that everyone else knows that you're dealing with the data and that they have to wait their turn. And so if no one else is doing that, then you will get that lock. If someone else already has a lock, the database management system is going to tell you to wait. Come back in a bit when everyone else is done, and then you can have your turn. If that's the case, good. You can do your stuff, and when you're done, you have to release your lock. But it also means that if you don't release your lock, you may end up in a situation where a database becomes inaccessible. We don't want that to happen. Locking leads to some other problems called race conditions. So we have to have some form of a protocol in place, and that's called a two-phase lock. And basically it means that we have a growing phase and we have a shrinking phase. In the growing phase, it means that first you collect all of your locks, so you make sure you lock all of your data, you do whatever you need to do, and then you release all of your locks. So lock first, release last. You can't go, lock a little bit of data first, then do some operations, then get some more locks, and then release one, and then get another one. That won't work with two-phase locking. So the whole point of this protocol, the two-phase locking, is that you first get all of your locks, do what you need to do, and then you remove all of your locks. So when we have these locks in place, we can look at this lost update problem again. Except now that at T1, we begin our transaction again, transaction 2. But we also immediately start asking for a write lock on the balance. And that means that at this point I'm basically signaling to everyone else, I'm going to make changes to the balance. You gotta wait. T1 at time index 3 also wants a write lock, but since I have it as transaction 2, it can't have it and it will have to wait. I can now make all of my changes and write them and commit them to the database and then unlock. Give up my lock, and at that point the lock can be granted to transaction 1, which is then going to read the value, but at this point it's reading the updated value. So what we've really done is we've spaced out the operation, so they're no longer happening at the same time, but they're offset a little bit, and the problem of our reading the same data multiple times has gone away. Now there's a situation called a deadlock, and basically the deadlock is the situation where you got multiple people pulling up to the intersection and no one wants to let the other one go first. Or maybe the other way around. Everyone else wants the other one to go first and you just sit there looking at each other. Eventually someone will have to go. But let's take a look at this situation here. We're beginning a transaction and then we grab a write lock at T2. Time index 2. The second transaction then begins and in time index 3 also gets a write lock on balance Y on a different field. The first transaction is updating the balance, writing it, and now it wants to go update the Y value, which we'll have to wait for. It can't because the X value already has, the T18, the transaction 18 already has that lock in place, so it has to wait for that to be done. Except that transaction 18 is trying to get a write lock on the other field. And so they're basically waiting for each other. And in a computer there is no such thing as, well, okay, I'll just go ahead. That's something that we have to tell the computer it's allowed to do. And at this point we have a deadlock. We can wait forever. Because A can't go unless B goes, but B can go unless A goes. And so deadlock is a bit of a problem with this. So how do we solve that? Well, there's no real good way. We could pick one at random and say, okay, I'm just gonna force one of the transactions to roll back, and by doing so I'm gonna release its lock so that everyone else can continue. But if that's the case, the question becomes which one? You're just going to pick one at random. If you're going to pick the one that started first but is only updating one field, while the second one could have been updating 100, that may have not been the right decision. Either way, this is the only solution, is to pick one that will have to roll back. And now which one you pick, well, that's a whole different story. Deadlocks are often caused by race conditions, which makes them even harder to debug. Anything that deals with concurrency is very hard to recreate in the first place, but especially deadlocks are very hard to even recognize, and when you recognize them, to find out what their root cause is. But in the end, you'll have to break one of the locks so that everyone else can continue. Which one is kind of a heuristic choice. You could choose the first one, the last one, the one that has the most impact, the one that has the least impact. You have to pick one. Okay, that's it for transactions. So the key lessons here are the ACID properties of transactions, the fact that transactions can lead to trouble, and that's why we need locks, but locks can introduce their own trouble through deadlocks that need to be resolved with transactions. That's the summary.